Okay guys, welcome back. Time for a new video. Decided to add a little levity to the situation based on maybe we should try and avoid looking at the news. Why shouldn't you mention the number 288? Because it's too gross. If you don't find the humor in that, look up the definition of gross, and that'll make sense to you. All right, what we're going to look at today is review of stuff that was already done in calculus. I'm sure you've gotten this far in calculus for those of you who are taking it this semester. Just want to click to get that away. If f at x and g at x are differentiable, then we know f times g prime at x is equal to f prime at x times g at x plus f at x times g prime at x. And what I want to do is show you an alternate to probably the proof that was presented in school. So the distance along here is f at x plus h, and the distance along there is g at x plus h. This is g at x, and this is f at x. So this little piece right here would have to be f at x plus h minus f at x. So the area, so I should probably do that one in blue. The area of this blue rectangle then would be this, which is f at x plus h minus f at x, because that's this length, times this length, which is g at x. So that's where that's come from. And now let's take a look at this purple rectangle. This dimension here is simply going to be f at x plus h. Now we're going to take a look at this dimension. What's this dimension? It should be g at x plus h minus g at x. And so to find the area, we're going to multiply that length by this width, just as we did here. Multiply length by a width. And then what's happening down here is we're going to take a look at, if you take a look at the area of this whole large rectangle like that, which would be f at x plus h times g at x plus h, and we subtract this one here, that would be created by f at x and g at x. If I subtract that area of that rectangle, f at x times g at x, what I would be left with are the purple and the blue pieces. So I'm noting that fact. If you subtract the area of the whole thing from this one, you will be left with blue plus purple. And now how are we going to use this? By definition, using first principles. The derivative of fg should be f at x plus h times g at x plus h minus f at x times g at x, all divided by h. And now I'm going to use this identity that I just proved visually in this picture. I'm going to replace this with f at x plus h minus f at x times g at x plus f at x plus h times, in brackets, g at x plus h minus g at x. So that's the area of blue and the area of purple. Then properties of limits will allow me to sort of split this in two. So instead of doing the limit of a sum, because we're breaking on that plus right there, I could do the sum of the two limits. So we've got the limit of f at x plus h minus f at x all over h times g at x, plus the limit as h goes to 0 of f at x plus h times g at x plus h minus g at x all over h. And now we have another property of limits that says the limit of a product. So I'm viewing this as one value, and I'm going to multiply by that. And over here I'm going to view this as one value, and that is the second one. So the limit of this product, this times this, is equal to the product of the limits. So there's the product of those two limits. And then I'm breaking this one up over here into the limit of this product, the product of that limit times that limit. And this, of course, is f prime. And that's just g at x. And this, of course, is g prime. So there's an interesting proof of that. Moving forward, if f at x and g at x are differentiable, you're familiar with the quotient rule, then the quotient rule says that f over g at x would be equal to f prime at x times g at x minus f at x times g prime at x, all divided by g at x squared. I do believe when I proved this in calculus, we looked at this. And I know I've told you the joke about the mathematician and the physicist. And the moral of that story was the mathematician tries to make it look like something they already know the answer to. So we sort of cross-multiply to bring that over. We had h times g is equal to f. And then we took the derivative, applying the product rule on the left-hand side. And then we isolated for h prime. Now I'm going to show you a different approach. So we're just going to go back to our first principle definition. If we're trying to find the derivative of this, probably should have little prime sitting there because I am trying to take the derivative of that. It should be f at x plus h over g at x plus h minus f at x over g at x. And what we're going to do now is get a common denominator. If I get a common denominator, I'll have that times that over here. I'll need that times that over here. So just getting a common denominator. And then what we're going to do is we're going to introduce this in the middle. And of course that is equal to 0. So we're not changing the value of the expression. Getting a common denominator doesn't change anything, and adding the 0 doesn't change anything. So now we have this, and here's the 0, and then we have minus that piece over there. This 0 was introduced for a reason because it's going to allow me to create primes. So I'm going to group, again, our limiting properties, right? I am going to break right there. So we've got a limit of those two sums is equal to the sum of the limit. So I've got this guy minus that guy. And over here I'm going to subtract a negative out of these two. So the negative is going to come out here. Notice there's a negative there now. So this becomes negative and that becomes positive. So now I've got on the next line the limit, because I'm going to now factor a g at x out. See, g at x is common between these two. When g at x comes out, I have f at x plus h minus f at x. And over here we're going to factor the common f at x out. When the common f at x comes out, we are going to get g at x plus h minus g at x. And I chose to write that term second. And now splitting along this line, like that. Like I'm seeing a typo there. That should not be there. So scratch that off. So now I'm going to split the product of this piece times that piece. Now remember, I'm viewing this as AB over CD is equal to A over D times B over C. So D can't appear twice, which is why that extra piece should not have been there. And on the next one, the way I would like to group it is I would like to group this to have the H. And then I'd like that one to be the second group and not have the H. So again, I'm going to split it into a product. So that shouldn't be there. That was an extra H. If I do H times H, I'm going to get H squared. I do not have an H squared up there. And again, H times H would be H squared, and I do not have an H squared there. And so now we've taken the limit of a product to becoming the product of two limits. The limit of a product, the product of two limits. And we set it up this way for a reason, because this guy right here is just f prime. When h goes to 0, you get g at x times g at x, which is g at x all squared. So I've got g at x over g at x all squared. This little piece here is going to become f at x over, sending h to 0, g at x times g at x. That becomes f at x over g at x all squared. And of course this guy here is just g prime. We already have a common denominator, so we now see that f prime times g minus f times g prime divided by g at x all squared. So that is our proof. Next slide. Chain rule, and then offering you a different proof than probably what was done in calculus for the chain rule. So if we have a composition of functions, f at x at g at x, and I want the derivative of that, it would be f prime at g at x times g prime at x. In class, I was in the habit of saying, take the derivative of the mother, leave the baby alone, times the derivative of the baby. Now, how can we prove that? So, first principle definition, we want to do the composite at x plus h and the composite at x. So that's going to give us f at g at x plus h minus f at g at x, all divided by h. And what I want to do now is multiply by 1 in this form. That divided by that is 1. And I am going to have to make this presumption, though. I cannot allow that to be 0 because 0 over 0 is not defined. So as long as this isn't 0, our proof is valid. And now I have the limit of a product, and I've already broken it up the way I wanted it to be set up, so I now can split this into the product of two limits, the product of this one times that one. This I can definitely see right here. I hope you can see that that's g prime at x. All right, now what are we going to do with this next little piece, right? Because this next little piece has f at g at x plus h minus f at g at x, all divided by g at x plus h minus g at x. So what I'm going to do is make this substitution. I'm going to say allow this denominator here to be k. And that's why that substitution went there. That k went right into there. Now I need a substitute for this, g at x plus h. So if I isolate this for g at x plus h, I will get g at x plus k. So I've now replaced that with g at x plus k. And the f at g at x doesn't change. Now when h goes to 0, k is also going to go to 0. Because if h goes to 0, I'm going to get g at x minus g at x. That, of course, is 0. So that forces k to 0. I now rewrote this as the limit as k goes to 0 of f at g at x plus k minus f at g at x, all divided by k. And, of course, this thing here would just be the derivative of f at g at x. So that's another handy little proof. And, again, this is how I talked about it in calculus. This was courtesy of Courtney Gibbons. She said when she learned this, the chain rule was differentiate the mother, leave the baby alone, and then multiply by the derivative of the baby. All right, some example problems here. So let's do this one first. Again, I'll pause in a second. You're going to decide, should you distribute? Is it better to use the product rule, quotient rule, or is this composition of functions? So I'm going to pause. Actually, we'll both pause together. You're going to do some work, and I'm going to do some work. Okay, now I'm back. We'll sort of discuss what we did here, or what I did here. I'm recognizing that that's a product. So I'm going to have to take the derivative of the first factor, which is 3x squared, multiplied by the second factor, plus the first factor multiplied by the derivative of this. Maybe I should show you, because you have to decide in university how much work to show. If you want to make it clear to the grader what you're doing, I guess I could have put d by dx of x cubed plus 5 times x to the 4th minus 6x plus 10 plus x cubed plus 5 times d by dx of x to the 4th minus 6x plus 10. So you can decide whether or not you want to put that step in, because by putting that step in, you made it clear to who's ever grading your work what you were doing. So that's how I determined that. That's how I determined that. I didn't have a discussion at first about massaging first. I suppose I could massage first. Massage first by expanding that. There would be 6 terms in that expansion. I could collect like terms. This is the correct derivative, and you would now in university have to decide how to proceed. What was the expectation? Should I expand this and collect like terms? I haven't done that here, but I'm going to leave that up to you to decide. Again, in university, take the direction from your prof. How should I handle that? All right, now I'm going to give you some time to focus on this one. We will both work together. I'm going to initiate pause. All right, so back now, let's discuss possibilities. One is if you don't like the quotient rule, you could massage and rewrite it like this. This would require to use the product rule, but because this exponent is nonlinear, right, that's not positive one, you're now going to have to use the chain rule. This is a composition of functions. This inner function, that's the baby, and then that would become the mother. I chose not to do that. I chose to directly use the quotient rule, and notice how I showed the greater what I'm doing. D by dx of the numerator times the denominator minus the numerator times the derivative of the denominator. And then on the next line, the derivative of that is -2 times that minus that times the derivative of this is 5x to the 4th minus 2, all divided by the denominator squared. And now you'd have a choice to make at this point in time. What is it you want to do with regard to simplification? Should I expand this? I guess these expansions don't look that hard, so maybe we should try these expansions. So -2x to the 5th plus 4x minus 6 plus 10x to the 4th. Negative times negative times negative. 2x times 2 is plus 4x. -3 minus 15x to the 4th. And then plus 6. All divided by x to the 5th minus 2x plus 3, all squared on the page. Now where are we? This should be a 5 right there. So -2x to the 5th plus 10x to the 5th is 8x to the 5th. Then I have minus 15x to the 4th. Let's see, we took care of that, took care of that, took care of that. Now we have that and that plus 8x. 6 minus 6. Those go. All divided by x to the 5th minus 2x plus 3, all squared. All right, now what would be the advantage of doing that? One advantage, especially if the question was asking me, where is the tangent horizontal? So I'm trying to find maybe an extreme value, because then I would need to know when the numerator is 0. And if I need to know that, I'm going to have to expand this and then attempt to factor. We can take an x out of this, and then I'd have to use the factor theorem. I'd be looking for candidates. Yeah, they would be plus all the factors of 8, all divided by the factors of 8, and then I'd move forward and see if that would factor. Again, you're going to have to take direction from your university prof. Are you allowed to leave it like that? Because it did take me some extra time to do this, and initially I had the wrong exponent written there, and I'm still not certain I haven't made any mistakes in that. If I had paper in front of me, I'd double check, or if we were in class, I'm sure you'd be correcting mistakes for me. You have to decide if it's worth the extra time, because time will be your enemy. All right, this one says find f prime at 0. So I'm going to let you try this one. And again, we'll both pause so that we can do some work. Okay, now we're back and we'll continue. We'll discuss sort of what I've written here. So I was running out of space, so I opened up a big square set of brackets because I couldn't fit that across. I chose to just take the derivative of the numerator, 9x to the 8th plus 8x to the 7th plus 20x to the 4th minus 7 times the denominator sitting here minus the numerator, which is sitting right there, times the derivative of the denominator, which is going to be 4x cubed minus 6x plus 2. Close this bracket now because I want to take this whole thing and divide it by the denominator squared. And now the question would be, should you simplify any of that? And I would say, no, you should not simplify any of that because they asked you to find f prime at 0. And look how easy it is to find f prime at 0. Plug a 0 in here, you just get -7. Plug a 0 in there, you just get 1. Plug a 0 in there, you get 0. Plug a 0 in there, you get 2. Plug a 0 in there, you get 1. And so -7 times 1 minus 0, all divided by 1 squared is -7. So in this particular case, there's absolutely no way in university you should be wasting time trying to expand all of that. All right, next question. You're going to work on differentiating this one. And again, all right, continuing, let me describe what I was working on. So I said I'm going to take the derivative of the first factor, times the second factor plus the first factor times the derivative of the second, just so I can show all my work to you. To take the derivative of this, I take the derivative of the outer function, which I like to call the mother, leave the baby alone. So it's 2 times 3x minus 5. I didn't write 1. And then I need to, because the exponent would become 1, times the derivative of the baby. Times that piece. There's that piece. The derivative of the mother or outer function becomes 5. And then the exponent becomes 4, and leave the baby inside. So this becomes f prime at g at x, where g at x is x plus 2, then times the derivative of the baby. I'm just coming over here, taking the derivative of that would go there. The derivative of that would go there. And then just cleaning up, 3 times 2 is 6, leave that alone, leave that alone. 5 times 1 is 5, leave that alone, leave that alone. Now we're going to factor. I can factor out that common binomial from these two, and I can factor out that common binomial from those two. So out comes 3x minus 5 times x plus 2 to the power 4. That's going to leave 6 times x plus 2 here, and over here it's going to leave the 5, and it's going to leave 3x minus 5. And then I'll simplify this. That's 6x plus 15x is 21x. 12 minus 25 is minus 13. Definitely would be doing this in university because that was straightforward. That wasn't a lot of work to factor out those. And now I can see where the horizontal tangents are. Right here. When that's 0, at the root for here, and then at the root for there. I'm going to clone the page. I'm going to clear the ink out because we have one more question here to think about. Alright, I'm going to pause as per usual, and then we will both work together. Okay, and now let's just take up this last one. So the outer function is right here. This is a power function, so the mother function I'm really looking at would be something to the negative 4. The derivative of that would be negative 4, taking 1 away from the exponent, negative 5. Leave the baby alone. But notice how I did massage the baby to write it as a power function. Instead of 2 over x to the negative 2, I wrote it as 2x squared. Then I need to multiply by the derivative of the baby. Those pieces come back down, and now the derivative of the baby, multiplying those two together, we'll get negative 1. Taking 1 away from that exponent, we get negative 10/3, and the derivative of 2x squared is 4x. And there's really no simplifying we can do here. For certain, you cannot distribute this here, because this isn't linear. If you wanted to, you could distribute that negative 4 through over here. And the last thing I want to talk about, I think I want to jump to this slide, because I want to talk about if you're going to be trying to earn marks, you need to help the grader out. What is the grader expecting to see? So let's look at this for a product rule. What the grader is expecting to see when they look at it is they're expecting the derivative of this to come first, and then that to come second. And then they're expecting this and the derivative of that to come second. If you write it that way, it makes it easier for them. So in a question like this, what are they expecting to see? They're not expecting to see the derivative of the baby first. They're not expecting to see the derivative of the baby first. They're expecting you to do the derivative of the mother, leaving the baby inside. So sometimes if you organize your work correctly, you'll get more marks in university, because remember, it's not the prof that's going to mark this, it's going to be a TA. And the prof is going to lay it out in standard form, and the TA might not notice that your answer is correct because you chose not to use standard form. Alright, that's it for today's lesson, and later on I'll try and post tomorrow's lesson, so enjoy.